Good morning, students. Now, depending upon the some queries and some requests by the students, I am making this new video about London equations. London equations effect. In previous lecture, we have studied about the Meissner effect. That when a specimen is placed within the magnetic field, it attains magnetization. But if the specimen becomes superconductor, then the magnetic flux lines are moved out of the specimen. That effect is known as Meissner effect. Now, but this is not exactly true. The Meissner effect suddenly not goes to zero. If it is some finite value and within the specimen, it does not goes to zero. Just as you have studied in your type 2 semiconductors, it gradually decreases to zero. Now the penetration depth is small, approximately equal to 500 atomic units. But if the specimen itself is of very thin thickness, just in case of thin films, which is of the order of nanometers. Now, in that conditions, the Meissner effect in thin films does not happen. To account for these two contradictory observations, we have to modify the electrodynamic equation in some other way to obtain the Meissner effect. Now, these modifications are known as London equations. Now, to understand the mathematics behind it, we have to start with the acceleration equation. Now, acceleration is force is equal to mass into acceleration. Now, the equation here, m dv by dt, this is the acceleration, is equal to minus ee. E is the electric field and minus is the charge on the electron which is moving within the specimen. Now, the current density is also defined as J is equal to minus NeV. Now, differentiating this equation of current density, we get this equation. Now, this is the condition of differentiation of current density. Now, putting the value of acceleration from the above equation, this equation, we get relationship between current density and the electric field, and it is defined by this equation. Del J by del T is equal to Ne square by m into E, where number of electrons per unit volume. Now this equation is known as the first London equation, which describes it shows that it is the possible to have steady current in the absence of electric field, because from this equation we have del J by del T is equal to some electric field into some values. Now if electric field goes to zero, that indicates as here, that indicates if electric field goes to zero, this equation equal to 0, del J by del T equal to 0. That means J is equal to constant. It is not equal to 0. Now, in ordinary conditions, the corresponding equations for the normal states is equal to J is equal to sigma E. That means current density is directly proportional to electric field. If electric field goes to 0, J goes to 0. But here, from this equation, it indicates that if electric field goes to 0, del J by del T equal to 0. That means J equal to constant. It doesn't go to 0. This is the condition. First London equation. Now we have the condition that taking the curl of both sides of equation, first London equation, we have curl of this is equal to curl of E. Now electric field has been separated from the rest of the terms. This equation. Now curl of E is equal to minus 1 upon C H, where H is the sum of applied field H naught and the magnetic field HB of the current density J. As J is equal to C upon 4 pi curl of H. Now differentiating this equation with respect to T, we get del by del T of curl of H. Now curl is mm, position dependent, and we have del by del T is the time dependent conditions. Putting these values in the above equation, we have curl of uh, putting this equation and this equation in this equation, we get a relationship between curl of H is equal to 1 minus 1 upon C H. Now we get C by 4 pi curl of curl H into this much. Now mathematics express this equation, integrating this equation with respect to time, we get as curl or del square are all independent of positions. These equations are independent of time. So we get these conditions where H naught is the magnetic field at time t equal to 0. Equation Now this equation is a direct consequence of Maxwell equations and the acceleration equation. This result admits the particular solution H is equal to H naught. On both sides, it will satisfy 0 equal to 0, where H naught is an arbitrary magnetic field existing at t equal to 0. But the Meissner effect tells us that we cannot have frozen in fields. That means we can't have any H naught which is initially at any time t equal to 0 within the specimen. But this equation says that this equation can have a solution which has H naught within the specimen. This now F London and H London therefore suggested that the acceleration equation be abandoned and we should take instead of as a fundamental equation. Now using this condition, now using this equation, here it was the condition. Now having the using this fundamental equation, which is postulated to replace Ohm's law in superconductors also. Now H is equal to curl of A, where A is a vector potential. Therefore equation converts to this much. Now we can compare this equation on both sides and we can have the value of A. We can have the value of A. On taking the curl of both sides of the Maxwell equations, we get 4 pi j by c is equal to curl H, and from this equation we can have curl of curl H is equal to curl of 4 pi j upon c. Now solving this condition, gradient divergence H is equal to del square H curl of this much. Now divergence of H is 0, so we get del square H is equal to curl of this much, and from above equation we have so this equation by putting the result of this equation from above. Solving this equation, we put the values as del lambda L ka whole square, where lambda L is equal to under root of this quantity. Now this lambda L is known as penetration depth. This is known as the penetration depth. Now this equation does not necessarily admit the former equation H is equal to H naught. Thus it is equation this equation. Now about we have the condition of solution of above equation can be has a simple harmonic conditions similar to that, and for that we have this general solution. Now H is equal to a e to the power x upon lambda L plus b e to the power minus x upon lambda L. Now where a and b are the constants, x represents the distance, lambda L is the penetration depth, Now, the factor, first factor e to the power x, predicts that h increases with x, which is contrary to the fact, because as we move inside the specimen, as x increases, the field should decrease to 0. But the first condition, being the positive exponential value, it indicates that it increases to higher values. But the fact is that it should decrease to 0. Now, this condition is satisfied by the second part, this part. That this second part indicates that h will decrease to 0 as we move inside the specimen. So, to remove this condition, we can assume or we can have the value of constant a equal to 0. Now, taking a equal to 0, we have only the fact condition left is h is equal to b e to the power minus x upon lambda L. Now at x equal to 0, h is equal to h naught, which is a constant. That means at the surface of the specimen, we have a constant value. And as we move inside, it decreases to 0. So this equation as our penetration condition depth. So to calculate lambda L, we can have a condition that is given by that h upon h naught is equal to 1 upon e. That means when x equal to lambda L, we have h is equal to h naught e to the power minus 1. So from that condition, we have this equation. Thus, the penetration depth can be defined as the distance into the superconductor at which the field value falls to 1 upon e times its value at the surface, which is equal to h naught. Now, the previous equations account for Meissner effect, which shows that a uniform magnetic field cannot exist in a superconductor. That is, HR equal to H naught equal to constant is not a solution of 11.31. Now I will send you the PDF separately so you can understand it better. Now, from the results of del square H naught equations, we can ensure that del square H naught is always 0, but H naught upon lambda L square is not 0 unless H naught is 0. Equation 11.27 ensures that j equal to 0 whenever h is equal to 0. Now, what are the drawbacks of this theorem? This theory, the main drawback of this theory is that although lambda theory explains the two conditions E equal to 0 and rising the superconducting state, it does not give any insight into underlying electronic process in the superconductors. So this is the only drawback of this theory, that it does not give any underlying electronic structure of the superconductors. This drawback was overcome by the theory proposed by Bardeen, Cooper, and Skrifer, commonly known as BCS theory, which gives a better understanding of the phenomena of superconductivity. Thank you.